So it says what's a monodatate ligand? It's a ligand that forms only one dative bond. I've shared everything, shared the notes on the group and the worksheet as well, the solved one and the unsolved one. So a ligand which forms only one dative bond with a central metal cation or a metal cation. So the observations, if you add a few drops of NH3, what happens? Blue precipitate is formed. What is formed? It's copper hydroxide blue precipitate. Why? Because when you add a few drops of NH3, the NH3 reacts with water and it produces OH ions and NH4 plus 1 ions. So when you add a few drops of NH3, it acts as a base, producing the OH ligand, which then reacts with the copper and forms copper hydroxides. When you add an excess of NH3, you get a deep blue solution. Why? Because the copper gets surrounded by ammonia ligands. Then you add an NaOH, you're gonna get a blue precipitate as well. Why? Because obviously copper hydroxide is formed, and when you add concentrate HCl, you're gonna get a greenish yellow solution. And why a greenish yellow solution? Because CuCl4 2 minus gets formed. Okay, is this clear? It's way clearer, Zaina. Is this clear?
Yes, sir.
Okay, and then he says this is about why changing the ligand changes the color of the solution. So it's about the D subshell splitting. TK, we wrote this answer over here in the notes. One second, where's the notes? TK, have sent the notes as well. So we wrote this. Why do the colors of complexes change? So the reason for that was with that when the why changing ligands. So different ligands, lone pairs have different charge density and cause a different amount of repulsion, and the energy gap that's created when the D subshell splits is different. And since energy is proportional to frequency, and it's a different frequency is absorbed, and a different complementary color is seen. So when the D subshell splits, you change the ligand, the repulsion that the D sub orbitals will have, that's going to be different, which is why the splitting would be different, the energy gap would be different, and hence a different frequency gets absorbed. Okay, is this clear? Clear? Yes or no?
Yes, sir.
Okay, next one is when chlorine, this is exactly the same. The color of the solution changes from pale to green yellow. This is exactly the same. It's now a 2 mark question, but the same exact answer. Here is asking you to write the K-stab expression. K-stab is the Kc for the equilibrium for the ligand exchange reaction. So it's product concentration, which is FeCl4, minus concentration. You don't write water in the expression, especially when water, everything is aqueous. And then you've got FeH2O6, concentration 3 plus, and you've got Cl minus 1 concentration, and that's power 4. So that's your K star value. He then says the K star value for this expression is 0.08. Calculate the concentration of FeH2O6 in the solution, which the concentration of ClIN is 2 mole. So everything is given. This is zero point 0.1. So they've given us everything. They've given us the K star value, which is 0.08. The FeCl4 minus 1 concentration is given, that's zero point 0.1. The FeH2O6 concentration is not given, and the ClN concentration is also given. That's 2 mole per dm cube. And that's power 4. So you're supposed to find out X. So you can just switch the positions. Can you try and solve what the answer is? Zaira, what's the answer to this, Zohair?
I got 0.08.
0 point? 0.08? Can you repeat your answer? Amna, did you try
Uh,
this? What's the answer?
0.0781.
0781. So I guess that's the correct one. But pretty simple, straightforward. Everything was given. What is meant by a transition element? What was a transition element? It is an element. It's just one mark. It forms stable lines with incomplete desorptions. That's what a transition metal is. And we're gonna skip the electrochemistry questions. We're gonna try and do this one, part C. So he says ruthenium forms complex ions, and in one such complex ion X, the ruthenium ion has a coordination number of 6. Each complex ion X contains one Ru2 plus ion, so it's got an Ru2 plus ions, and it's got one Cl ion and one SO2, and the remaining ligands are NH3, so there would be 4 NH3s because there's going to be one Cl, there's going to be one SO2, and there's going to be 4 NH3s. So the overall charge will be 1 plus because this is 2 plus, this is minus 1. Remember, it was an octahedral complex. It had a coordination number of 6, which means the number of coordinate bonds it's forming. State what is meant by the coordination number of 6. It's the number of coordinate bonds. And state, so then you also have to state the formula of X including its charge. So that's this. I mean, you're not going to write the inner charges. It's you write the overall charge. So you'll write RuCl, then SO2, then NH3 times 4, and the whole thing has a charge of plus 1. So this is it. Now, next one is draw the two isomeric forms of X in the boxes below. Your diagram should show. So you have to draw two isomeric forms of this. The two isomeric forms are that because it's an octahedral complex, so either the Cl ions and the SO2 are together or they're on opposite sides. So it's a cis transform. So I'm going to draw the first one. So either the Cl and the SO2 are right next to each other, and the NH3s are on the other side. And the overall thing is plus one. Or the other one, which is that it's going to be, so the other one is, those are your X, Y, and Z axis. So the SO2 and the Cl will be opposite to each other. So that's the other one. So cis and trans together, and this is opposite side. TK, is this clear, this part?
Yes, sir.
So what type of isomerism? That's geometric. Cis trans. And explain the origin of the color in the, so that's the same thing. You have to write exactly the same thing for 3 marks, which we've been, so define the term transition. It's pretty much the same straightforward questions. It's an element that forms stable ions within complete d subshells. Compare the melting point and density of iron with calcium. So obviously you just, it's a one-line answer. They're not even asking for the explanation. Both are going to be higher. Complete the electronic configuration of Fe2 plus. We can do that. Explain the origin of the color in a transition element complex. Now it's a 4 mark question, so that's exactly going to be the same, which is that, where's the original definition? This one. That due to repulsion of lone pairs on ligands, the d subshell splits into two energy levels, electron from lower energy d subshell orbitals gain energy and move to higher energy d orbital. And the energy gap delta E matches frequencies from the visible spectrum since E is proportional frequency. Hence, a complementary color is seen. So sometimes it's 2 marks, sometimes it's three, sometimes it's four. Now state the shape of this complex. That's six ligands, so that's octahedral. Write the equation for the reaction between FeH2O6 and an excess of Cn ions. Now, so it's Fe with six H2Os. And there's Cn ions coming in. So what would be formed? They've written the equation. They've told you what the answer is. It's Fe with Cn6. And the six water molecules get knocked out. And then he's asking us to deduce the oxidation state of Fe over here. So it's going to be done exactly the same way that we normally find oxidation state. It's X. Cn, we know it's -1 times 6. And the overall charge on the complex is -4. So it's going to come out to be +2. Over here, it's Fe is X. Cn, I know it's -1 times 5. And NO is 0. And the overall charge is -2. So if I solve for this, +5 goes to the other side, so that's going to become +3. ठीक है, is this clear? Zohair, Amna, Zaina, is this clear?
Yes, sir.
Yes, sir.
As a monodentate ligand, again, it's a ligand that only forms one coordinate or dative bond with a metal cation in a complex. Complete a diagram to show the three-dimensional structure of the Fe. So that's an octahedral complex. So you're going to draw this. So it's five CNs and there's one NO. And the overall charge on the entire thing is -2 or 2 minus. Again, the two complex ions are different colors. Why do changing ligands changes the color? Because different ligands have different lone pairs have different electron charge density, which is why they cause different amount of repulsion, and the d subshell splits with a different and the energy gap between the lower and the higher energy d subshell is different. And since E is equal to energy is proportional to frequency, a different frequency gets absorbed. Okay, to find the term coordination number, it's the number of coordinate bonds that are complex forms. He says E shows, this is E, it shows both optical and cis trans isomerism. One isomer of E is shown, C2O4 ion is represented as OX. In the boxes, draw the three-dimensional diagrams to show the trans and the optical isomer. So the trans one is, this is the cis isomer. Both CLs are on the same side. So he's drawn the octahedral complex this way. So we're going to follow it. So dotted and there's one on the z-axis. So in the other one, the CLs will be on opposite sides. And the ox with the bidentate ligand, that's going to be over here and over here. Is that clear? Is this clear? Amna Zain, is this clear, Zohair?
Yes, sir.
And then there was an optical isomer. The optical isomer was the mirrored version. Remember, there were two types of isomers. You had optical isomers. Optical isomers were only formed when you had an octahedral complex, and they were forming data bonds. Sorry, with bidentate ligands. So they would form two mirrored versions, right? And so these were your optical isomers. So if I want to draw the optical isomer for this, I need to draw the mirrored version for this because he was asking for a trans and he's asking for the optical isomer as well. So I'm going to draw the mirrored version. So everything has to be mirrored properly. So everything has to be mirrored really neatly. So the CLs are now on the right side. And this ox will be on the left side. So, and the other ox would be on the right side. Okay, that's your mirrored version. Is that clear?
Yes, sir.
Yes, sir.
As the next one, we've got explain what is meant by the term polydentate ligand. So it's a ligand that's capable of forming many dative bonds. With the same metal cation in a complex. So that's what a polydentate ligand is. And we did one polydentate ligand, which was eta. I think it's this one. This is eta. Eta had a charge of I think -4. Eta was actually -4. So that was your eta molecule that it would form from all sides. Its atoms would come from all sides. It was one big molecule. And they will all these atoms would surround the metal. The metal would be stuck in the middle and of the molecule, and it will be forming direct bonds with all of them. So this one is about eta basically. He's drawn eta, and he's given you an equation as well. So now you have to figure out what you need to figure out is the K star for that. So it's product concentration, so it's CD and EDTA, and the whole thing has a charge of 2 minus concentration. That's the product. You don't write water in the expression, divide by the reactant, which is CD with H2O6. That's 2 plus, and then there's eta. 4 minus concentration. And the units are going to be its mole per dm cube divided by mole per dm cube multiplied by mole per dm cube. So it's going to be x minus 1. So it's going to be mole per dm cube minus 1. So the unit will be mole minus 1 dm 3. Is this clear?
Yes, sir.
So here's another one. He's saying that the K star values for two ligand exchange reactions are given. And an equilibrium, a fourth equilibrium is set up between these two complexes as shown this one. So he's asking, write an expression for K equilibrium 4 in terms of K star 2 and K star 3. So you have to find out what this Kc is. I mean, K equilibrium is basically Kc. In terms of this, so I'm gonna write those expressions first. K star 3 is basically what? It's CD En. So it's CD En is twice. Here, let me erase this first. Okay, that one. So it's CD. En is twice in H2O twice. And 2 plus. So the product concentration divided by the reactant concentration. So that's CdH2O6 and 2 plus. And En is going to be squared. So that's the expression for the second one. And the first one is, for the first one, it's going to be a big expression. It's going to be CD with CH3NH2 4 times H2O twice. So its concentration, and that's 2 plus. Divide by the reactant concentration, which is CdH2O6. And the other one, CH3NH2. And that's power 4. So that's going to be power 4. Anyways, we've got these two expressions. So I just need to somehow figure out the expression. It's just a 1 mark question, by the way. So what is the expression for this one? In terms of K stab 2 and K stab 3. So I think this is the numerator. So it's going to be K step 2. And this thing is in the numerator denominator for this. So it's going to be divided by K step 3. I mean, you can write the whole expression, but you'll get the same thing. That if you write the expression for this, it's this expression getting divided by this expression. You'll get the expression for this. Is that clear? Zoe, is this clear? Zaina, Amna, is this clear?
Yes, sir.
You can write the whole expression. So it's and that would come out to be this divided by this. The rest of the things, yes.
Sir, I'm so sorry, but will you send like the solved PDF when you're done?
Yeah, I did. Just one second. Let me just check. Yeah, I've sent it actually. I've already sent it.
Okay, I'm so sorry, sir. Thank you. I'll look through the group.
Okay. And then this one, calculate the value of Gibbs free energy delta G for equilibrium equilibrium 4. So how do you calculate delta G? Delta G, if you remember, was delta H minus T times delta S, right? So delta H is given, that's 0.840, minus the temperature is given, that's 298, and the delta S is also given, that's 80.9. But it should be in kilojoules, so I'm going to divide that by 1,000. You solve this and you'll find delta G. Is that clear?
Yes, thank you, sir.
Okay, I'm going to skip the delta G part because that's define the term complex ion. That's an ion formed when what happens when the central metal cation natively bonds with ligands. So this one we've done what happens when copper reacts with NaOH. So this is cobalt. So it's going to form cobalt hydroxide. Copper and cobalt will have exactly the same reaction. You can write the ionic equation for this, and the type of reaction, that's precipitation. It's cobalt H2O6 that is pink colored. You add OH ions, and the water gets knocked out. All of the ligands, they get knocked out, and you get a brown precipitate of cobalt hydroxide. No, not a brown precipitate. You get a blue precipitate. And the type of reaction, that's precipitation. And then with ammonia, it's going to be color would be with ammonia, that's a brown solution. And the ionic equation would be that this thing changes to cobalt with surrounded by NH3. Either four NH3s, it could be any number of NH3s. You could have NH36 as well. Now that's a ligand, that's going to be a ligand exchange reaction. Okay, any other leash? He says use Lee-Shatler principle to suggest the expected observations when silver nitrate is added dropwise. Now, when you add silver nitrate, it's going to react with Cl ions, and they will form AgCl solid. So the concentration of Cl ions will decrease. Hence, your equilibrium is going to shift backwards. So you're going to write that the equilibrium shifts backwards, and therefore the color of the solution would go from blue to pink. Is that clear that cobalt with chlorine was was blue and this is pink? Is this clear?
Yes, sir.
Okay, then you have he's asking you to draw the two isomers. So this type of stereoisomerism. Well, it's NH3 6 and Cl, sorry, NH3 and Cl3 as well. So that's the same thing. The only difference now would be that the NH3s will not be together. Two of the NH3s will be making an angle of 180 degrees, while the Cls will also not be together. The Cls will be on opposite sides. Is this clear? And that's geometric, right? Is that clear?
Yes, sir.
And suggest why one molecule of X can form four dative bonds because it's got four lone pairs. It's got four nitrogens and four lone pairs are available to form dative bonds. Just a one mark question, that's it. Now he says this reacts with cobalt ions in a 1:1 ratio to form a new complex ion. Construct an equation for this. So they react in 1:1. So cobalt with six H2Os reacts with this entire thing. That is C6H18 NN4. Now remember, this forms four dative bonds, right? So it's going to replace four of the water molecules. So C6H18 NN4, and there'll be two H2Os left. And the two H2Os are going to get knocked out. ठीक है, remember this would form four dative bonds, so you don't need four water molecules anymore. So four of them would be gone. Four over here, sorry. ठीक है, is this clear?
Yes, sir.
Okay, what's the meaning of the term degenerate? Degenerate means that they are the same type of orbitals having the same energy. Like px, py, pz are degenerate orbitals. State two of elements that have one electron in the 4s, that's chromium and copper. They have one electron. Over here, he's asking, sketch the shapes of the atomic orbitals from the d subshell as shown. In an octahedral complex, the d orbitals split into two different energy levels. Write an H in the box under each of the orbitals at the higher energy level. So when in an octahedral complex, if they split, where's the splitting? When they split, it's harder to keep electrons on the axis in an octahedral complex. So the orbitals that are on the axis, they will be at the higher energy level. So which is why it's going to be which ones are on the axis? This one and this one. Is that clear?
Yes, sir.
बस ठीक है। चल ठीक है, let's continue tomorrow then, right? Okay then, take care.
Thank you, sir.